based on what you wrote, the note that I gave you, tomorrow, Monday, 3 p.m., 3 to 4, let's have a tutorial. This Akshay here.
So Monday, tomorrow, 15.
There is an exam in
What exam?
Oh,
What exam?
no, okay.
I asked you when you have available time.
No, it's okay.
Uh-huh.
No, it's okay.
To be a tutorial. Look, I owe you one lecture. Plus, I told you that I'll add possibly a few more lectures because we should cover kosmology. I'm serious about it. Unless you tell me you really don't want to.
Was it really called it?
I don't know. I think this is automatically recorded.
No, it's unscheduled.
What?
This is
So
unscheduled.
you do it now.
It will be here in this lecture hall, and it's all automatically recorded. Here. Another thing regarding that is that Akshay asked you, he said that he told you that, he asked you to write down your homework in English, if you don't mind. Yeah, because it's a bit difficult for you to read Hebrew. You can read Hebrew, but you will not understand, so it's a pity. Happens, starting to lose students. Okay. So, I told you it's going to be fun. A quick recap on what we did. So we basically completed the discussion about the principle of equivalence. What we did last time was really two things. We showed the equation of motion, the geodesic equation. Right, is derived from a correlational principle. Right, so it is the shortest path. This is physics. The equation is what you get when you take the shortest path in terms of minimizing the proper time between 2 points. You end up with the geodesic equation. We did it twice, both for special relativity and once in general relativity. Then we spoke about the Newtonian limit, what's called the weak field limit. And we basically showed you that in the weak field limit, which was defined as small perturbation, space, slow,
And
stationary in time, right? Does not change, the gravitational field does not change in time. We end up getting back Newtonian the result that you know from Newtonian mechanics, which is quite good. Otherwise, we'd be unhappy. I guess.
that we can know the effect of the mass itself, the body of the log mass.
Yeah, that's a standard for a test particle. When
I
we speak about test particle, we always mean that the particle itself does not affect its environment. Right? The question is, what is a test particle? That depends on the problem at hand, right? My mass is very small relative to that of the Earth. Right? So when I look at my motion as a person in the gravitational potential of Earth, it's negligible and not affecting it, right? The Earth's gravitational potential is negligible relative to that of the Sun. If you have two binary neutron stars that rotate one next to each other and produce gravitational waves, then we can no longer assume that it's a weak field approximation. Okay? That's why it took many years to solve this problem, because you cannot use this approximation. And then we start to speak about vectors and tensors in curved spaces, in curved space-time, which is more what we're going to do today. And what we spoke about is the principle of general covariance. And the principle of general covariance essentially states that if we have an equation that we know is correct without gravity and special relativity, and we know that it does not change its form when put gravity, then we know it's correct. Okay? And this really follows from the principle of from the equivalence principle, and that emphasizes the importance of working with vectors and tensors. Because with vectors and tensors, we know exactly how to transform them from one coordinate system to another coordinate system. Okay. Not all. We know how to transform vectors and tensors. We need to still know how to transform derivatives of vectors, but we'll get to that. All right. Any questions? No, that means everything is fully clear. I'm sure you're going to get 100 in the exam. That's no questions to me. That's what it means. Yes?
How do you know when the weak limit phase? I mean, at some point, we neglect some terms, and if we would take them into account, there would be small numbers somewhere in the metric. But could it be that at some point they will have a non-small effect? I mean,
it's the same question of when can you use a Taylor expansion, basically. Right?
Only more complicated because there are.
Conceptually, it's the same thing. Mathematically, maybe it's more complicated, but conceptually, it's the same thing. When are you allowed to use a Taylor expansion to expand the function? Right?
Well,
if the function is well behaved, if it's not, it doesn't have a pole or anything close to that.
Yeah, but if you take a Taylor extension up to the 10th term, you can have a limit on the tail of the extension, and the limit can be calculated.
No, only if you know analytically your function. Only under certain conditions. If your function have various spikes, if it's bounded, right?
We
Your
always
function
talking about
your function has to be bounded. It has to be nicely behaved in order for that to be true. So the same is here. Practically, there is no real question because we are only dealing with nicely behaved spaces. Okay, but essentially it's the same. It's the same idea. Like, if you're getting close to the black hole, it's not going to work. If you get far away, then it's okay. Very and wavy speed. But we'll get to that. We haven't spoken about black holes. We need to get to a few steps before we get into black holes. So let's go over them. Okay. Vectors and tensors in curved space. So we spoke a lot about vectors and tensors, but it was all in the concept realm of special relativity. And now we need to generalize the discussion into curved spaces. And we say that the vectors belong to the tangent space. That's true, but the question is, how do we define that in a curved space? Right? The real problem is that when you have a curved space, we're losing the notion of direction. Right? What is the direction of a vector in a curved space? Think of it for a second. You cannot really define it properly. So we need to think of another way. Right, we did say that a vector is associated to a single point. Right? But what is the direction of a single point if the space is curved? It could be curved in various ways. That's okay. So I already said, I already gave you the final result. I'm going to prove it to you, and it's a little bit mathematical. It's one of the most mathematical parts of this course now. So if you do not follow the math all the way through, then remember the last point, the bottom line. The bottom line is a vector is a directional derivative. Vectors are directional derivative. Directional derivative is generalization of the concept of a partial derivative. Partial derivative meaning that you are taking all the coordinates fixed except one. And you're looking how a function evolved when all this this one. And the directional derivative is the same, but along the same path, which is not necessarily following a specific coordinate system, a general path. Okay. In order to do that, we need to first define what is a manifold. Now, I insist on not defining it to you, because it's very mathematical, so that's what Akshay will do tomorrow. It's mathematically, there are several steps to do it, but intuitively it's very simple. Right? Intuitively it's what I said. Manifold in our world is a space which locally looks Euclidean, but globally is not, or not necessarily. Euclidean space is also a manifold. Right? A space that locally looks Euclidean, but globally is not one. It's a hand waving, but it's a hand waving which is good enough to capture the essence of things, right? So, you know, space that doesn't have any spikes, right? Doesn't have like this is not
What's happening in black hole?
What? That's
hole.
not a legitimate manifold for us, right? From, you know, from a physical perspective, this is not, right? But a ball, the surface of a ball, like the surface of the Earth, is a legitimate manifold. Right? It's called a Riemannian manifold of genus 0. It's the technical. So, two-dimensional Riemannian manifold of genus 0. 2D Riemannian manifold of genus 0. That's a technical name. Right? And a bagel use a two-dimensional, the surface of the bagel, right? But the surface. Again, always think of it in terms of ants, right? Hey, I know it's a bagel. No, if you're an ant, you don't necessarily know it's a bagel. You don't necessarily see the bagel. Now, we know that the Earth, we can treat the surface of the Earth as a two-dimensional surface, which is true. I mean, if I had to go to America, right, I'm forced to travel on the surface of the Earth. If I take an airplane, it's a tiny bit above the surface of the Earth. I cannot go straight to America. With the shortest path from here to America, of course, will be just like that, but I cannot do that. Right? I'm forced to live on the surface of the Earth, right?
You can try.
I can try. It will take me much longer than if I take an airplane to get there, or even if I take a boat, right? But then I'm forced to go on the surface, right? Now, if that, you know, if you're still not convinced, think of the universe as a whole. We don't really have a way of getting outside of the universe and know what is the exact, what type of manifold it is. We are stuck inside the universe, and it's going to stay like that for I don't know how long. Right? I can think of a double bagel. Then I'll get it's a two-dimensional Riemannian manifold. This will be genus 1. This will be genus. Etc. Now, given that we have a manifold, we want to put some structure on the manifold. And something on top. Okay. Metric, we don't need, by the way, we don't even need a metric on the manifold. Manifold can live perfectly fine without a metric. Don't worry, we'll always use a metric in this course. Don't need that. And now we can think of all sorts of crazy manifold, like, you know, the Mobius strip manifold. Forget it, it's non-orientable manifolds. Let's not discuss it here right now. Okay. Any questions about the idea of a manifold? Again, a mathematical definition, actually I will give it to you, it will take 1 hour and you get the exact definition. And it will look exactly the same as what I just said. will be mathematically correct. Questions? No. Okay. So now let's try to put vectors on a manifold. The issue is I want to construct a tangent space of vectors using only things that are intrinsic to the manifold. I cannot go outside of the manifold. Okay? I have to be careful in what I do. So this is my manifold. I have a point P. Okay. So the vector is defined at the point P on the manifold. But I want to define the vectors using only things intrinsic to the manifold M. How do I do that? Okay, so there is some.
All the direction of gravity.
Right, that's essentially what I'm going to do, but let's see how it works. Right, so we know that there is this thing which are called tangent vectors to a curve. So the first thing I do is put a curve. I call the curve gamma and I specify it by some parameter lambda. Typically it would be one of those lambda, right? So lambda equal to 0, 1, 2, 3, 4, whatever. The way to think of that curve, mathematically, this curve gamma is a map from R to M. Right? Lambda specifies a number, it's in R. Right? Every number R gives me a point on M. 5 is the point P in this example. So really, the correct way to think of it is I have some map from R to the manifold. Okay. Now we can think of many such curves. Think of another curve. Goes through P. This will be another curve. That, right? So I can think of a vector as being a tangent to the curve at that point P. Right? And set of all of them make a tangent space. But I haven't really defined it, so I can't really do it. But that's a real problem. But the point is, we need to define what is a tangent vector to a curve. Still ill-defined at this point. Okay. It doesn't help us defining it. It says that we can put a curve. Now we can do something else on that manifold. So that's the first step. The second step, I'm going to erase that. Still have my point P here. And I can assume that there is some coordinate system which I can put in the vicinity of P. It is allowed. Why?
Because it's Euclidean.
Because close enough to P, it's going to be Euclidean, right? So I can say that will be x1, and this will be x2. Once we define the coordinate system, when I put now a curve through P, gamma, there is a lambda here, right? Lambda equal to 0, lambda. then I'm really defining, this curve defines an element to adding coordinate system in the vicinity of P. Any curve through P defines an element of Rn. What is this element? Yeah?
Sign numbers.
Right. dx mu over d lambda. Right. Have your n coordinates x mu. So the curve would just say how they change at p along the curve. Right. I mean, if the curve goes exactly in the direction of x1, what will be this Rn set? If the curve at P goes along this one, we have dx1 over d lambda 0, 0, 0. We're getting there, but I still have a problem here. What's my problem? I don't like to use coordinates. I want to define vectors in a way which is coordinate independent. So I'm nearly there, but I'm not going to use that approach. Right? The issue is we want something. But we want a coordinate independent definition. If you follow the logic, now we're pretty much there. Right? We said that specifying the coordinates, the coordinate themselves, right, they specify a map, right? A map from M to Rn in the vicinity of this point P. Right? Once I specify coordinates, it's really a mapping, right? At any point in M, I give it n values, right? Rn. That's the meaning of coordinates.
So we assume it's an n-1 manifold in Rn in an n-dimensional space.
Sorry again?
כאילו אנחנו רואים שזה ירידה n פחות אחת במרחב n-מתי.
No. Once I specify the set of coordinates, right, the number of coordinates is going to be the dimension of M. Right, this is two-dimensional, so I'll have two coordinates. Right? But I can think of the coordinates conceptually. When I put the coordinates, right, I'm mapping each point on the manifold in the vicinity of P. I give it a set of numbers. That's what it says here, right? Every point now is specified by a set of numbers. How many? N, right? So it's a mapping from M to Rn. That is the true meaning of a coordinate. Right? I have a space here. How do you know where this point is? Somewhere in this space, right? When I put a coordinate, oh, this has an x and y. That is the meaning of a coordinate. Right? Put a coordinate system, so I'm mapping M to Rn. Yes?
Since the mapping is only defined locally,
Yeah.
it's not one-to-one, right?
It is what I want.
in the vicinity of
In the vicinity of the point P.
in the entire manifold.
I don't care because I'm defining now the vector space.
You've written it as a function from the entire manifold.
No, I don't need. I'm defining now the tangent vector at P. I want to define now vectors at the point P. Okay. Now, in fact, I can generalize this idea. If you get this idea, we can generalize it. So the generalization means that we can specify, rather than the coordinates specify a mapping from M to Rn. So I can think of the set of the space of all functions f from M to R. Right? Defined near P. So I'm going to call that F, capital F, the space of all functions, smooth functions. From M to R. Right? It's called C infinity. It means that it has infinite number of derivatives. It's well-behaved functions. Okay, it's completely abstract what I'm saying now, so you have to use a little bit your imagination. So it's called C infinity map. F maps F from M to R. Now, what is the curve? What does a curve do? It is an operator. What is an operator? What does an operator do? Take one function and converts it to another function, right? So a curve is an operator, again at P, in this space. What does it do? Take F and convert it to the F d lambda at the point P. Which is what I care about.
Wait.
What?
So how do you define the derivative in M to R space?
No, I don't define a derivative M. F is
How do
a
you
function.
define smooth function?
F is a smooth
How do you-
function on M, and any smooth function on M. Right?
You mean
And I can
smooth
think of it as a
topology?
mapping from M to R. So every,
And how do you define smooth function?
it has infinite number of derivatives.
How do you define derivative from M space? M spaces.
It doesn't really matter right now. That's not the key issue. The idea is that the function is well behaved, right? So it's a continuous function. It is when I go from any point, again, why it's not an issue, because again, when I get close enough to P, it's going to be a Euclidean. Okay? So I can define function in Euclidean spaces. Right? Similar to the coordinates, right? Coordinates specify a mapping from M to Rn. So I can think of any other functions which specify some mapping from M to R. And the set of all functions is a space. And it's defined in the vicinity of the point P. Right? And I can think now of any curve as an operator in this space. I take any function f and convert it to the f d lambda. Yes?
The arrow you draw is from a function to a point, or you mean that it happens
No, at the point
every
P. F at P.
Okay.
So somewhere at the point P. I only care about the point P.
But you're doing it as a function going to a function.
Yes.
So it's
It's a function
all
to a
P
function,
in a way.
yes. The whole concept is I need to define it only at the point P. Right? The vectors belong to the point P. That's not a change. Yeah?
The operator takes a function, it returns a function.
Yes.
So the function it returns takes a point P and returns the direction of the derivative.
No. The function it takes, the function
What's
is
the output function?
some number.
No.
Some number.
It's
Like,
so
take the regular derivative. You take a sine, right? You take the derivative of a sine, it's a cosine. What's the
Right.
output? It's a number.
Cosine
no,
is a
it's
function.
a function.
It's sorry. The output of the function is a number.
Yes.
The output of the derivative is another function.
I'm asking what is the function? It's defined. You define it in the point P. How
The
is
function,
it
no,
defined?
the function has to be defined in the vicinity of the point P, which I can always do.
Okay.
The function is defined in the vicinity. It doesn't have to be defined here, right? This could be quite
How
far.
is the output function defined?
What?
How is the output function defined?
The f over the lambda.
Okay, but
In
What I-
the point
Ah,
which is
yeah,
not
okay.
P.
when the point is not
Okay, I don't have to define it here. But I really need it only at P.
Okay.
Okay? Right. So now I can finally make the claim. So the mathematically correct claim is that the tangent space TP, so the tangent space TP is identified with the space of all directional derivative operators along curves through P. That's the correct mathematical definition. So, if you want to prove that, you need to show proof 1 that this is a vector space. And 2 that this is the vector space that we actually want.
How do you define it? How do you define the vector space that you want?
Let's prove that. So it has to have the same dimension sound, which it does. You have to show that we're gaining. What we really want is to gain back the notion of direction. Okay. Now that we have this tangent vector space, right? We want to have this notion of direction. So it's going to be mathematics, but at the end it's going to be quite straightforward. And the direction is along this curve. So, how do we know this is a vector space? It's quite straightforward, right? If we have two elements of this vector space, right? So, element of this vector space is what? E over the lambda, E over the eta. It's an element of this vector space. What do they represent? Derivatives along two curves. Right? I have two curves. I don't have directions. I have two curves. Right? This is specified by lambda. This is specified by eta. Right? So here we can write x mu of lambda. Here we have x mu of eta. So obviously we can add them and multiply by real numbers, which means that a b over the lambda plus b over the eta is also a vector. Right? New operator is also. Belongs to the same space. Now we need to check that it closes. The space closes. How do we check that? meaning that the new operator is a derivative operator itself. How do we know this is a good derivative operator? Yeah, it's linear, it obeys Leibniz rule. So I have A d over d lambda plus b d over d eta that acts on two functions f and g. It's exactly what you'd think it is. AF dg over d lambda plus ag df over d lambda plus b f dg over d lambda plus bg df over d lambda, which is a df over d lambda plus b df over d eta. What did I do? Plus b df over d eta g plus a dg over d lambda plus b dg over d eta f. So the product rule satisfies Leibniz rule. So you satisfied.
What is this group?
What?
What is this?
Product rule.
The close?
Yeah, I want to show that the space closes, namely that when I have a new operator, it also belongs to the same space.
So you just need to show a curve that.
Actually, yes, but I do it algebraically rather than put a curve.
But G and F are function of what parameter?
Sorry?
G and F or
G and F are functions that are functions of the manifold. They are defined in the vicinity of the point P. Okay? General functions. So for the second question, is that the vector space that we're interested in? Obviously the answer is yes, otherwise I wouldn't bother.
Wait, so how do you define a lambda and eta?
What?
How do you define lambda and eta?
Lambda and eta are the curves, are the parameters along the curve.
Okay.
These are the two curves I have. What I want to say is that if I take the derivative along one curve, derivative along two curves, I take a linear combination of them, I get another operator which is also belongs to that same space. So the space closed. That's what. So how do we know that this is really the vector space we want? Well,
You define it.
What?
Or this is how you define it.
pretty much, but the simplest is maybe to find the basis for this space. What will be the basis for this space? So is this a space that we want? Find the basis. What does it mean find the basis, right? I have the point P. And now I can put coordinates, right? Because the basis is arbitrary, I do it the way I want. Let's say I have x1, x2, then I'll put the vectors of d1, d2. It's called, by the way, a coordinate chart, coordinate system. This is a coordinate, just for the, it's called a coordinate chart. What is a chart? It's a mapping. I think the only way to think of it properly, when you have a manifold which is curved, right, is to think of it in terms of mapping from the manifold, from the point on the curved manifold into R, or Rn. So a coordinate chart is a one-to-one mapping from an open set U to Rn. U is an open set that's an open set in Rn. You're familiar with the concept of an open set? Yes? Anybody who's not familiar? Should have seen it in one of your calculus. Okay. So once I specify a coordinate chart, then there is an obvious basis which has n vectors, which will be what?
Euclidean basis vectors.
The partial derivatives. So the basis and directional derivatives along the coordinates namely di. Oh, sorry, d mu. Now I can argue that this set d mu is a basis for the tangent vector space dp. D mu, move that. D mu is a basis for TP. How do I show this is a basis? I have to show that.
And different elements.
First set n elements, right? So n elements. In terms of dimensions, I'm good. And then
Independent
Independent
space.
space.
that it spans the space, right? That any element I can write as a linear combination of these verses, right? So again, I'm thinking again of manifold. I have here a curve. I have a point P, and I have a curve gamma from R to M. And F, function F is defined here from M to R. And lambda is the parameter along the curve. Lambda equal whatever. So we have the operator d over d lambda, which I can expand in terms of the partial derivative, expand in terms of the partial derivative. Right. So df over lambda is a what? It's a lim, where epsilon goes to 0, of f at the point x mu lambda plus epsilon, right, minus f of x mu lambda divided by epsilon. Yeah? How can I write that? I can simply expand that and write that as d x mu over d lambda d mu f. Just use the chain rule for that. That's true for any function f. So we have that d over d lambda is just dx mu over d lambda d mu. Which is what I wanted. Show that any element of the tangent vector space can be expanded in terms of the basis vectors. what is this vector? This is the tangent to the curve gamma. Okay, or you're too confused by now? This is the over d lambda.
It's a vector that because if you have a vector that is tangent twice, the vector is also tangent.
What?
יש לי וקטור שככה זה יפר אותו בקבוע, עדיין משיק. יותר לא פרמטר.
Yeah, you can multiply that. That's what is this? Dx mu over the lambda? What do we call this? What do we call this? Yeah, what? Lost you. How do we call that? These are the components. Right? These are the components of the vector d over the lambda in the basis d mu. Okay? It's very similar, from here on, it's very similar to, nearly from here. It's very similar to what we did in special relativity. But now we generalize it to any curved spaces. Right. In special relativity, we had V. In special relativity, rather than d mu, we had E mu. Right? That was essentially all. Now this, the name is just a coordinate basis. Because we use a set of coordinates to generate it. Now, we don't have to have coordinate bases. We can have non-coordinate bases as well. We just handy for us. Okay? Look unhappy. Normalize, etc. Now, once we do that, what about the transformation now? Leaving it here for a second. What about the transformation now? So we set here coordinates x1 and x2, right? We can set another coordinates. So this will be the point P. Now we can set a different set of coordinates. Right? X1 prime, x2 prime. Now the new basis vectors would be d1 prime and d2 prime. How do we transform? D mu prime is that?
dx mu to dx mu prime.
That's all. Dx mu over dx mu prime, dx d mu. What about the transformation of the vector components? Right, we had v d mu d mu. What happens to the vector when we're changing a basis? Nothing, right? What is the vector now? Right? Remember, the vector would be the curve here. Right? What happens to the curve? Nothing. It's the same curve. We just change the basis. Right? So I have v, the vector, which is v mu is equal to v mu prime d mu prime. D mu prime is dx mu over dx mu prime d mu. So it's v mu prime dx mu prime over dx mu. What I do? D mu prime.
The prime is supposed to be like down.
Yeah, down. Sorry. Dx mu prime d mu. Yeah, of course. So if we take that, then v mu prime is what?
dx mu prime.
Dx
mu
prime over dx mu v mu. How is that different from what we did in special relativity? Nothing. There is a slight difference, but I mean, mathematically it looks the same. But there is a key difference here. What did we do in special relativity? We transformed by Lorentz transformation. Right? This is a linear transformation. Right? This is more general. It doesn't have to be a linear transformation. It doesn't have to be linear at all. Right? So linear transformation is a special case of what we're doing here. Yeah.
You must know only how the curve transforms, right?
How then?
How the curve transforms, how the coordinates of the curve. How
The curve does not transform. The curve is the same curve. It's a chord. Remember, the whole concept, the whole point is that the physics do not care about the coordinates. It's our choice of coordinates. We selected to do the coordinates like that. We could have selected them like that. It's okay. Nothing happens to the physics. The vector does not change. It's how we describe the components of the vector in this new coordinate system.
And the question is, we only need to know how the coordinates of the curve transform. We don't need to know how the entire space transforms.
You mean locally? Yes, because vectors are defined at a point. So we're only looking at the vicinity of the point P.
It's not the vicinity. I'm talking just the curve which we define.
The curve does not change.
No,
Curve
the
is the same
coordinates of the curve.
The coordinates, we select the coordinates in the vicinity of the point P. Okay? I think you understand. Right?
Yes.
We select the coordinates at the vicinity of the point P. It's meaningless to select them somewhere which is very far away. Right? This is a flat, nearly flat board, right? In this class. If I extend this board until Australia, it's going to be nonsense, right? It's going to be quite. But in this class, it's perfectly fine to say this is nearly flat.
My question is, we only need to know how the coordinates of the curve transform. We don't need to know how the coordinates of the entire neighborhood.
I disagree with the term coordinates of the curve.
The components of the curve.
The components of the curve, yes.
No, we only need to know how the components of the curve.
The components of the curve, as described by a certain set of coordinates, are changed. Yes.
We only need to know how the components of the curve. No, we don't need to know how the entire coordinate system around P changes. We only need to know.
No, the components of the curve are affected by the coordinates that we select in the vicinity of the point P. So we first select the coordinates in the vicinity of the point P. It's local, it's not global. And then, only then we can say how the components of the curve change. Okay? This is, of course, the transformation law of the covariant vector. This is transformation law of a covariant said, it's compatible with the Lorentz transformation that we had in special relativity, but now it's more general. It's, it doesn't have to be a linear transformation, but it's any general transformation that we have. I'll give you an example shortly. Transform from Cartesian to spherical coordinate system. So it will still work. Okay, what about covariant vectors? So again, covariant vectors belong to the cotangent space, TP star. Right, so TP star, what is that? It's a set of linear maps, omega from TP to R. Yes?
That we got the transformation of a variant vector?
Contravariant vector.
Yes.
Contravariant vector. Thank you. My apologies. What's the canonical example of one form or covariant vector?
What does it do to any basis?
What is the canonical example of that? We discussed that.
Hatana.
Gradient. Right? Example, gradient of f. Example,
Is it the gradient?
gradient of f, which we write how? Df. What is the operation of the f on a vector? The f that operates on the vector d over d lambda. Sorry, it's full derivative. D over d lambda. The f over d lambda. Nothing else that we can really do.
Next point B.
Okay, now again there is a small subtle point, right? Why do I have to use the gradient of f and not f itself? It's the basis for example of a one form. The reason is that I want something that is defined only at the point P. And f needs to be defined everywhere if I want to take its derivative with respect to it. The gradient is defined at the point P, which is what I want. Right? That's a subtle thing that you need to think of. Right? Gradient, any one form, is defined at the point P. Does not depend, its value does not depend on any other location. On M. That's key here. So I have to use the gradient. So, and very similar to the partial derivative along some coordinate. Then the gradient of the coordinate function provide natural basis for the cotangent space. The gradients of the coordinate function x mu provide a natural basis for the cotangent space. Remember that when we spoke about in special relativities and flat spaces, right? How did we use that? We wrote down that theta mu that operates on E nu was equal to what? Delta mu nu, right? In SR. Yeah. So we can use the same philosophy. Analogy. Dx mu that will operate on d mu. It give us a what?
Dx mu to the
D
mu.
D nu. Okay, when I make the thing. Dx mu over dx mu, which is a delta mu. Of course, any arbitrary one form, omega, can be expanded as omega is omega and mu dx mu. There's nothing else much we can do. Yeah. So again, the transformation properties of the basis of the dual vectors. Dx mu prime. Nothing too much that can be done here. What will it be? Dx mu prime over dx mu, dx mu, of course. And the components? Omega mu prime. The opposite, right? Dx mu over dx mu prime, omega mu. It's pretty much the only thing you can do. So this is the transformation law of the components of covariant vectors. It's okay? Yes?
Why should dx mu be? Why don't you get the delta according to delta right now? Can't coordinates depend on other coordinates? Like when we have a spherical coordinate system or something?
Orthonormal.
No, it's the same that dx mu and dx nu is the same vector, just with other, like in the dx mu tag, it's a different coordinate system.
Yes, that should be clear, right? When I'm using unprimed, I mean it's the same coordinate system, just I'm looking at different coordinates, and when I'm using primed, it's a completely different coordinate system.
Yes. But
That should be clear.
don't we have, if you're looking with saying, okay, this is
Look at r theta and phi, right? dr over dxr over dx theta. It's 0, right? They're indeed orthogonal.
only the basis coordinate vector, not the coordinates themselves, because
The basis coordinates, yes. I'm choosing as a basis. Yeah? What about tensors?
to define the same way.
Of course. thing is that once you get the idea, there's nothing really you can do. You just follow exactly the same rules. So tensors. So I can expand a KL tensor. My T would be T mu1 mu k mu1 mu L. But then just I can write it in terms of the outer product or tensor product. D mu1, that's a symbol. D mu2, D mu k, D mu1, dx mu1, dx mu L. This is called an outer product or a tensor product. It's a notation that you'll encounter once in a while. Basically, that works on different spaces. What happens on the coordinate transformation?
Each coordinate is transformed.
Of course. T mu1 prime mu k prime mu1 prime mu L prime is dx mu1 prime over dx mu1 dx mu k prime over dx mu k. Now, of course, the opposite for the lower indices, dx mu1 over dx mu1 prime, dx mu L over dx mu L prime, and then t mu1 mu k mu1 mu L. It's pretty straightforward, right? The transformation for each component, and the inverse for each lower. Questions? Yeah.
Why is there x from there for the news but not for the
D mu is a shortening of d over dx mu. We don't have a similar shortening for the x. Yeah. So guys at the back. Yeah.
Can you repeat it the next? Why does it d mu k and dx mu on the upper and the t in the second?
It's a notation.
So what's the difference? What's this?
D mu is d over dx mu.
Okay, and what is dx mu?
Nothing. Just dx mu.
Dx mu.
Mu.
Ah.
Never. Just a notation. Yeah.
Because this is a vectors control variant. This is the
Yeah, that's all. Okay, examples. I'll give you an example so that things might get slightly clear in your head. It's very abstract, but at the end of the day, it's very straightforward and it's not pretty. It is exactly aligned with what you're used to do. I just gave you the theory behind it now. You know, basically know it intuitively. Okay, let's take a 0 to symmetric tensor S. Example. Symmetric 0 to tensor, which we call it S. Right. Two-dimensional manifold. write it as mu nu x 0, 0, 1. I can write it as s equal s mu nu dx mu dx nu. So, what is written here? This is x dx squared plus 1, say dy squared. To this, I write it as an x and y. Now I want to change coordinate system. Just randomly x prime is x to the power 1/3, y prime is e to the power x plus 1. How would you do that? So we need to express the old basis in terms of the new basis, right? Old basis in terms of the new basis. X is x prime cube. So dx is 3x prime squared dx prime. Y is ln y prime minus x, which is x prime cube. And so dy is 1 over y prime dy prime minus 3x prime squared dx prime. We just need to plug these expressions directly in here. We do have to be careful because it's not guaranteed that things are symmetric. So, in a sense that dx prime dy prime does not have to be equal to dy prime dx prime. Generally, x prime dy prime is not equal to dy prime dx prime. We have to be a bit careful in what we're doing, though here there's no problem really. So S is x dx squared, so we have okay, plus dy squared, so I have to square all that. I ended up, after a little bit of algebra, 9x prime to the 4, 1 plus x prime cube dx prime squared minus 3x prime squared over y prime dx prime dy prime plus dy prime dx prime. As I said, generally they don't commute, so when I add that, I don't have to, I don't automatically add them. Plus 1 over y prime squared dy prime squared. Just like in here. Yeah. Square that, you get this minus 3. What you have here. So I can write it as s mu prime. Put it back in the matrix form. Right, so I have 9 x prime to the 4 plus x prime cube. Then the x prime dy prime will be minus 3x prime squared over y prime minus 3x prime squared over y prime and 1 over y prime squared. It's pretty much what you do. You transform, make a transformation of basis, right? Nothing. Just a second. So most of other things we did in special relativity is not going to be affected, except three things which we're going to spend time. Partial derivative, the metric tensor, and the Levitz beta. And we're going to start by looking at that. But before that, questions? Yes?
Is there an intuition why it should be symmetric in this case? The after transformation?
Not really. Generally, it is not symmetric, but you know, when you just write it down, when you expand that, just have to be careful making sure that you're not commuting them. This is a symmetric because it's a very simple. You can think of more complicated transformation.
If S is symmetric in one basis, it's symmetric always, or not? Not necessarily.
I don't think so. I don't think necessarily. I have to think of that. Not sure. Don't think it is. Questions? Okay. Now we're starting to get into the fun parts. Work hard, but now comes some fun parts. If no further questions, then I told you there are a few things that we need to know, which are different between the flat space-time, special relativity, and curved spaces. So the three things I said are derivatives, the metric tensor, and the Levitz beta. So let's start one by one. Actually, I'm going to start with the metric tensor. So volume element and tensor densities. Volume elements in curved space-time and tensor densities. First, I told you, not everything is a tensor. What about the metric? What about the metric? G mu. It is a tensor, right? Obviously, it is a tensor, right? G mu nu is eta phi eta alpha beta d psi alpha over dx mu d psi beta over dx mu. Fine. How to transform it? G mu prime eta alpha beta d psi alpha over dx prime d psi beta over dx mu prime. So eta alpha beta this I can write as d psi alpha over dx mu over dx mu prime, d psi beta over dx nu, dx nu over dx nu prime. But this is just g. So this is equal to dx mu over dx mu prime, dx nu over dx nu prime, g nu. So metric is a tensor. We knew that. So g mu nu is a covariant tensor. What about its inverse? Not covariant, not a problem. G mu nu contravariant. What about delta? What about it? It's a mixed tensor. It's a mixed tensor. What about gamma?
Not tensor.
That is not get to that. What about the determinant of G? So I'm going to define it now. Another non-tensor quantity is a determinant. G is defined as minus the determinant of G mu nu, which is also written as the absolute value of G mu nu.
Why the minus?
What? Why? Why do I need the minus?
There's only two quantities.
What? Yes. Right. So, if we use the transformation law of the metric, so use transformation law of the metric tensor, which is just written right here. Then what do we get? G of x mu prime is the absolute of the x mu prime over the x mu to the power minus 2 G of x mu. Right? When I take the determinant, this is something which you may remember from your linear algebra. You see that in your linear algebra? What is that, by the way? I don't know if it's in your algebra or some other question. Jacobian, right? Where did you learn Jacobian? Calculus. Calculus? Which year?
2 or 3.
What? 2 or 3? Okay. This is Jacobian, right? This is Jacobian. You can write this G prime equal to dx prime over dx minus 2 G. So G, the determinant, transforms like a scalar except this extra factor of the Jacobian. Scalar plus Jacobian, this is called as scalar density. G is known as a scalar density. And this term up here, that's called the weight. So we said that G is a scalar density of weight minus 2. G is a scalar density of weight minus 2. Why do I care? For various reasons. I'm going to show you one of the coolest ones right now. You want to guess? What happens when I make a coordinate transformation to a volume element? Picks up a Jacobian, right? So when transforming coordinates a volume element, D and X picks up a Jacobian. Dn x prime is dx prime over dx mu dnx. So what does it mean? invariant volume element, what am I going to do?
One will depend on the square root of G.
Great. So square root of G in X is an invariant volume element. Which is quite cool. For example, 3D space written in spherical coordinates. How do you write this 3D space in spherical coordinates? What is a line element? What is a line element? The S squared is the R squared plus
2D space is 3D space.
R squared, d theta squared plus sine squared theta d phi squared. Right? What is the metric? G mu nu.
R squared and R squared sine.
1 R squared sine squared theta. Yeah? You all see that from here?
Not the inverse.
No. Why the inverse? It's symmetric. dr, d theta, d phi.
Why is it G mu mu?
No. No. What is G? The determinant.
About 4.
R to the 4 sine squared theta. What is an invariant volume element? Invariant volume element. Square root of G, dr, d theta, d phi, R squared sine theta, dr, d theta, d phi. Okay? Magic. Yeah? You've seen that before. Now you see where it comes from. Okay. Okay. Just a notation. I don't think we're going to use it much. Right? If we put a metric, if we can write the metric notation, if we can write the metric as G mu nu is a diagonal. First we put all the minuses, then we put all the pluses, then we put all the 0. Then we say this is a canonical form. Canonical form. If we have zeros, any of the eigenvalues are 0, then we say it's degenerate. Use that. And if it's a degenerate, what does it mean? We cannot take the inverse of a degenerate metric. Yeah? And if all the signs are positive, then we call the metric Euclidean. Riemannian. If we have single minus, then we call it pseudo-Riemannian. Another name is Lorentzian. And here we always have pseudo-Riemannian matrix in this course. Okay. Questions? Okay. So I think I can stop here now. We're going to do some more maths on Thursday. So first of all, tomorrow you have a tutorial. We'll give you the exact mathematical definition of a manifold, and you're going to work hard for 1 hour, and then you see that it's exactly what it is. Intuitively, but it will be correct mathematical structure. Then on Thursday we have some more maths, but after that we'll gain a lot of strong tools that we could start playing with, and we could start to see things in a different way, like these things. Any further questions? No? Okay, so I see you all on Thursday. Do you know if there are other people who registered that did not show up today for any reason? We're sort of converging to the... Okay. I'm not sure it's going to get simpler. We're going to continue along the same path pretty much. The really fun part comes after we... I told you, the course is basically split into half. The first half is where we derive Einstein's equation. It's going to be a lot of heavy maths, a lot of heavy concepts. The second half we're going to solve it. That's going to be the fun part, because that's when we're going to speak about black holes and about the Big Bang and things like that. So that's why I prefer to add a few more lectures as needed to not skip the fun part. Alright? See you on Thursday unless you have any further questions.
יכול לבקש שהייתי מתחיל בגול של הקשיבה.